All right. So for the last lectures, I want to completely switch gears, start talking about things like distributed systems and distributed object systems. Now, I got some question about security just before the class started. I might pick it up a little bit later. One thing to be aware of when we talk about distributed file systems and distributed object systems is, in fact, security. I mean, this is one of the major issues everywhere. So you should be worried about security whenever you send any bits over the network. You either send stuff that's completely in the public and then you try to optimize for performance alone, or you should be worried about security and then pretty much guard everything. But all right, so let's start talking about file systems. And let me remind you that we already had a little bit of a discussion, but maybe a month and a half back. The idea being modern operating systems have very clever ways to abstract away the notion of a file. So what a file is, it's very much dissociated from any physical representation. That opens up the way for very deep integration between so-called distributed file systems and normal operating systems, right? Basically what it means is that you don't necessarily need a distributed operating system to have distributed file systems, right? So this was a big discussion, a big battle going on, and one of the authors of the textbook, maybe both of them, Tannenbaum, was involved in Amiga OS and a stream of distributed operating systems. A big argument he was trying to make is we need these operating systems that understand distributed communication, right? And offer distributed one or another kind of guarantees deep in the operating system. It didn't turn out to be that way. The normal, regular operating systems with networking, in fact, through middleware, can provide what distributed operating systems are promising to provide, right? But the distributed file systems are a little bit weird because most of the time they can actually be deeply integrated in the operating system, right, through the virtual file system interface that I mentioned a long time back. So we're going to see a little bit of that later. But of course, the first question is, why have a distributed file system? I mean, what are some of the benefits? Why bother with the distributed file system, right? And it's a little bit strange because file systems are really low level and to some extent ancient kind of technology, right? So some of the first proposed ways to organize information was into files, and now suddenly 40, 50 years later, we still have files flying around, right? In the meantime, we had all kinds of other cute abstractions, including databases. I mean, databases are really not files. I hope you understand that, right? They might use files at the lowest level, but they don't necessarily have to. For example, the database I'm working on does not represent data in files. Uses raw hard drives to represent the data. There is really no clear benefit in using files to do something like databases. So there are other abstractions. For example, relations in a database, the collection of relations, which is the database itself and so on. They don't necessarily have to live on a file system. Most of the time they do, and that's sometimes just because people have to see what's behind the scene, right, arguably. That turns out to be a little bit harder sometimes when it comes to distributed file systems. Okay, so what are these distributed file systems good for? Well, one of them is some sort of common shared availability to the file system. We use this all the time, right? So you have your home hosted by the CIC department somewhere. What does hosted mean, right? And suddenly you can access your home from another machine. What does exactly that imply at the lowest level? Well, it's in fact a form, or it's precisely a distributed file system, right? So somehow you can access the files on the remote server on various machines. That's one of the things that distributed file systems are all about, right? So simply availability is one reason to have distributed file systems. Another one, obviously, is redundancy, right, and fault tolerance. The moment you can move things away from the client, you can contemplate, as we've seen in the rest of the class, the possibility to, in fact, do some sort of replication that will allow you to be fault tolerant. So if one of the copies goes down, you still have the other one, and still have availability, right? So if you use other techniques, for example, backups, right? Backups do not guarantee availability, because in fact you have to take the system offline and go and find stuff in the backups, and it can take sometimes forever depending on how old the backup is to recover such a file, right? So you might get your file, but in a month. That's highly undesirable versus it's there. So think, for example, using distributed file systems, which in fact they are used all over the place, using distributed file systems, for example, to serve as the backbone of an application like Gmail, right? So you're a Google engineer, you have to start designing something like Gmail, and you have to ask yourself hard questions about where do those emails go, right? It's very easy from user's point of view, right? When you click on an email, it magically shows up on the screen. Where is it coming from? Where does it leave most of the time? How comes when I log in with another web browser or I go on a very different machine, I still access the same emails? What kind of guarantees the system has or doesn't have, right? So from the point of view of a system designer, when it comes to providing various kinds of services, you have to figure out where are you in fact going to store the information. Traditional way to do this is in some sort of a database. But then you need a replicated, powerful, possibly distributed database to basically deal with the deluge of requests you're going to end up doing. And then, of course, the question is how do you design those kind of databases? Google took a very different approach. And early on, they tried to keep it very simple, right? So early on decided that, in fact, it's better to put your money on a distributed file system rather than to do it through some very sophisticated object store, data store, or things of this sort. Okay? And then they just started building a very good distributed file system, in particular, extremely scalable distributed file system, and then everything else was piggybacked on such a distributed file system. This is very different than a database approach in which you go and design a database in which, again, files are just something that might be underneath, maybe or maybe not. But in fact, you have maybe a full-fledged SQL access to it and full-fledged transactional semantics, right? But that's not really what Google tried to do. Now, even before I go into some of the details, I want to give you some idea of who's actually doing these distributed file systems, right? Another extreme, so almost anything powered by Google, in fact, it's stored in GFS, Google File System. There are other enabling technologies, but the storage itself is Google File System. Then Yahoo itself, well, I mean, we have to talk a little bit about this. I hope to at least have a lecture on this about MapReduce. How many people here bumped into MapReduce at all in any class, right? So it's kind of the darling now of pretty much everybody, right? So the MapReduce, and in particular Hadoop, which is the prominent open source implementation. By the way, Google invented, I mean, nobody invented MapReduce. MapReduce is a very old idea, right? The MapReduce function showed up in Lisp in the 1960s. The first MapReduce framework, in which those are just the primitives, popped up in about 2004 at Google, and Google people had a paper about this. But their system was a Google private, not available to anybody, because it was considered key technology. A company like Google has no incentive to, in fact, make such technology widely available, because that means they're just going to have stronger competitors. Nevertheless, Yahoo people panicked and said, hey, that's a good idea. Let's design our own. And they started to work on Hadoop. It's rumored, Google never made it very clear. Well, I think their initial paper suggested that their implementation was in C++. Hadoop, it's actually in Java. But the important thing is both of these systems, and probably mostly because of the Google heritage, both of this system, MapReduce system, in fact use a distributed file system as the basis to distribute information in between multiple sites. So distributed file systems turn out to be a key technology if you want to simplify the problem in a certain way. And the big thing about distributed file systems is everybody knows what a file system is. They use it for the last 20, 30 years, right? I mean, the moment you start using a computer, you first learn how the files work, and then you learn some other stuff. So it's extremely accessible kind of technology. An object store can be very, very tricky. A database is extremely sophisticated, right? We teach database classes, and people still can't properly do something with that. But if I ask people, yeah, move a subdirectory from one part to another, or delete a file, create a file, and whatnot, I mean, that's stuff that's taught in the 101 introductory class. Now, that doesn't mean that distributed file systems are simple, okay? But they at least are attempted to be simple. So a particular strategy when you're trying to do some large-scale redundant application is to have a distributed DFS at the bottom, and then rewrite whatever is it that you have on top to translate into operations on the distributed file system, right? So it's weird. It's actually used, and for distributed file systems is basically the pillar of how things go. You can use the distributed file system as a way to communicate with other sites. I mean, think about it. I can literally create a file, put the information in a file, and if it's a distributed file system, presumably whoever wants to communicate with me has access to it as well. They can just hunt down for that file and read it. So I could use other means to say, whatever I want to tell you, it's in this file, and then can go and use the distributed system facility to open that file and read the content. Now, this has a tremendous advantage, because any distributed file system is designed to deal with enormous files, and the entire capacity of a distributed file system. It's not uncommon for a distributed file system, to now have a petabyte or more of storage, right? So you're talking about a petabyte, at least, now, storage. And files easily can be terabytes in size or more, right? Now, obviously, the question is, how do they do this? And this is what this series of lectures are going to be about. But the point I'm trying to make is, once you have this kind of a facility, certain things that otherwise would have been a nightmare become reasonable from the point of view of the middleware writer, right? So I could, for example, compute a very large result, put it in the distributed file system, and just let somebody else know, hey, that's where your file is, and then they can, essentially by accessing the file, get access to that information. Now think about, for example, the actor model in which you would send a message from one party to another. It's going to be a nightmare, because this kind of very large resources, you cannot do perfect coordination in any way, shape, or form. Now at some point, at a very low level, there's going to be some sort of coordination between somebody, right? But not at the high level. And obviously, the application designer only cares and will write against the high level. So then, some of the benefits are, for example, when the file is accessed and how it's accessed is completely dissociated from the act of producing the result. This results in very clean, simple middleware code, which is highly desirable, because otherwise you never sort this out. So kind of a lesson here is the following. If you really need to move large amounts of information around, a distributed file system might be the thing for you. Right? You can still use other forms of communication so that you let somebody else know where to look and what to do. But ultimately, the file system itself, the file system paradigm, might be perfect for this kind of a purpose. Okay? So we'll come back to this as we go along. But let me just give you an idea of, for example, how Google is doing something like Gmail. Right? So what you can do is basically, you can decide to store very little things or very large things. It's probably better if you're storing at least slightly larger things. And that has something to do with how distributed or any file system can be implemented efficiently. But for example, what Google can do is simply load in memory from the distributed file system the secret files corresponding to your email. And this is how it's serving the email. Right? The main advantage is you can have. This is kind of an interesting idea. So traditionally, you would think that there is a server that will provide a distributed file system, and then you have many clients. But in fact, the solution Google adopted is very different than this, and to some extent, under your nose, but nevertheless very clever. And in particular, all of these machines, in fact, participate both in the distributed file system, which happens to be called GFS, as I mentioned, for Google, and HDFS. Is it no? It's not HDFS. HDFS for the Hadoop file system. Anyway, it's one of this. Probably HDFS for Hadoop. So the same set of machines will act both as clients and participate into this distributed file system exercise. So one hallmark of distributed file systems is that, in fact, these files, whatever they are, will reside on multiple machines at the same time, right? So we want to dissociate even any notion of location for these files, because ability to move resources from one machine to another, right, can both allow you to implement some sort of redundancy, and at the same time, various forms of load balancing, if that's what you want. For example, if you notice that part of your network is used a lot more than another, you could try to shift some resources around and deal with it. Right? Now, when it comes to Let me see what slides I have. Maybe I should stick to the slides. Okay, so there are basically two fundamentally different models when it comes to distributed file systems, right? Some people have tried some hybrids, right? So one of them is this one, and this is what you would expect, in fact. The client and the server, the client sends absolutely any request with respect to the file system. We'll come back in a few slides what those requests are, mentioned before though, right? Another model is, in fact, a full caching model in which the client says, you know what, give me the existing version of the file, then I'll work on it for a while, and then I'll send you back the new version of the file. Okay? In this way, the server, first of all, the entire file is transported, and the server is only involved in move it to the client and move it back. The server has to be a lot more active in here. So what kind of actions are we talking about? Right? Well, this table is in the context of NFS, one of the oldest distributed file systems. What kind of actions are we talking about? Well, some of the options are things like create, link or create a symlink, make directory or make node, rename, remove directory, and then things about the files, right? Open, close, lookup, whatever, set attributes and get attributes, right, and read and write. Now, of course, most of the activity is probably going to be on these reads and writes. So you do want to do some sort of file manipulation, and then this reads and writes to the file, because that's kind of the bread and butter of what a file system is supposed to do, right? Allow you to write files and allow you to read files. Directories are just a way to organize the files. And to a large extent, you could even argue that you don't really need directories, right? I mean, it's kind of maybe a controversial issue. Humans like to organize things in directories, but the directories are not particularly efficient at doing so. The trouble is the same file can actually be viewed from many points of view and be useful in many different contexts. So instead of dealing with a different facility, maybe search-based, you have all of this stuff that, in fact, it's a hack, namely links and symlinks. So if you really want to make a file visible in 3 directories, you do either a link or a symlink. Anybody knows what the difference between a link and a symlink is? Right, so I mean, it has more to do with the implementation, but it's never only implementation. It's also about future behavior, right? So a file really has 2 things in it. And this is the way I want you to think about even distributed file systems, right? A file has a way to get to it, so it has metadata. I mean, it's not only files. Lots of other things have metadata and data. And you can, in fact, choose to represent them in very different ways, and even in completely different places. Now, usually they're implemented in the same place and with roughly the same mechanism, but it's not a requirement by any means. So what's metadata? Things like file name, maybe some ownership rights, right? Owner, all kinds of things like this, but it's just information about what the file might or might not be. Part of the metadata can also be where is it into some sort of a hierarchy. It depends on how hierarchies are actually implemented, right? Most file systems don't have, the file doesn't know where it is, but somebody else knows where the file is. And the data is simply the content of the file, right? So the difference between a symlink and a link is basically a link would replace the metadata with another set of metadata, but point to precisely the same data. Okay, that means once you do the linking, it's impossible to tell which was there first. It's simply 2 heads on the same body, okay, deep in the operating system. A symlink is just a special kind of file that's interpreted in a special way by the operating system. It just happens that that file is basically contains just a string which contains a full path to where the real file is. Okay? Now, links have significant limitations because it's impossible to have different heads on the same body unless you're part of exactly the same file system. Okay? Which means if you create, for example, if you have 2 hard drives and you create 2 different file systems on the 2 hard drives, you cannot actually create a link that has the head on one file system with the body in another file system. It's just not allowed because it's implemented at a very low level. Symlinks, sky is the limit as long as you can have some sort of a symbolic representation for how to get to it, right? Also, if this file is moved in another directory, right? The link file itself, like any other regular file, it can still access the same body because it just has those internal pointers. That's not happening with the symlink. If you move the file underneath the symlink, now it's hanging. It's impossible for a link to be hanging, right? But it's very possible that a symlink is hanging, and you see this all the time. For example, in Linux, in which somebody left some link there. Actually, the operating, if you ls, when it uses colors, will paint it in red if it's a hanging symlink, right? So symlinks are truly pointers, but the links are not. The links are basically this. Well, internally, everything is a pointer, but the links are a deep connection between the metadata and the data, and it just happens that you can have multiple heads. Well, usually, in metadata in Unix file systems is stored in inodes, and data is stored in blocks or data nodes. Okay. Well, it just happens that usually the inodes and the D nodes use exactly the same underlying storage. This is how most file systems do things. Not necessarily. So some of the more advanced file systems can actually not even use inodes at all. Organize this exactly like you organize a database and just have the data itself live into some sort of blocks. Now, that leads to an interesting idea, right? Namely, you could dissociate the metadata from the data. You could, in fact, use database-like technology or search-like technology to find files that have a certain metadata, as long as you can establish this connection between the metadata and the data. And you have a lot of freedom in what is it that you do with the data. In particular, nobody says that the data should live on a single machine or a single device. Right? The trick is the low-level code in the implementation of the file system to have the ability to hunt down where all the data pieces are. Also, this is where you would do things like redundancy. Right? So here's, for example, the idea in GFS, and there is some slide later. Before that, since I have a slide here, let me just briefly show you how the NFS works. Right? NFS is deeply integrated into the virtual file system, right? So on the client side, right, you have this is the upper layers and this is the lower layer. In between, you have a network, right? So you have your application sitting on top through the system call there. It's going to make a system call, and it's trying to access a file. It goes directly to the virtual file system. The virtual file system essentially keeps track of how the virtual file is mapped into the real file. And it either goes to possibly one of the local file systems, because the virtual file system corresponds to that, or it goes to one of the distributed file systems, for example, NSF, in which case what you have here, it's a more complicated setup. It's a full-fledged NFS client, some sort of a remote procedure call, and the counterpart on the server, in which you're going to have the server and the opposite side. Now, obviously, files have to be stored somewhere. So the preferred way to store files, even to store pieces in a distributed file system, it's in fact local file system. So this is kind of a weird, maybe twisted notion. Okay, but you don't have to do this. It's just convenient, right? So most of distributed file systems are implemented by piggybacking on top of regular local file systems. For example, in GFS, that's precisely what's happening, or in NFS for that matter. In NFS, there is a local file system that lives on the server that is exposed through this kind of a mechanism as a distributed file system on the client machine. What that means is the following. When a request happens on the client, the request is in fact sent through the wire and executed against the copy on the server. Right? Now, of course, some information has to go back in order to provide this illusion in the virtual file system. Right? But the virtual file system, it's an abstraction. Everything is some sort of an illusion. Right? So essentially, if you say list the files in a directory, the client can make the request, it goes on the server executes it against the local file system, and simply computes the result, and exactly the kind of result you would get from the local file system, or something that can be converted into that, and it goes back. And the moment it's presented to the client, it's presented in exactly the same way as if the file would be local. There is really no way to tell, right, in a direct way, if in a modern operating system, of whether the file was local or the file wasn't local. I mean, sometimes large latency and whatnot might give you a hint that something wrong is happening, but sometimes the local hard drives are hiccuping, so then you can have long delays. So even that's not a good indication. Okay? So as long as you get the right answer, you can in fact delegate finding the answer to somebody else and bring back the answer. That would happen, for example, on a write, let's say. You want to write something in a file, you simply would take the entire content of what is it that you want to write. We need to to zoom on that in a second. NSF client will take over, tells the server, hey, you have to write this portion in this file. It's actually writing it. So on a subsequent read, again, the read goes through this kind of a channel, and of course, the answer is supposed to come back. The read request goes one direction, the read data comes the other way. Right? Now, obviously, you can have multiple such clients connected to the same server. As long as the server doesn't trample over it itself, and it shouldn't because it has a local file system, everything is going to be nice, except that you have some latency involved in accessing these files, and potentially network bandwidth problem if you're really transferring large things. Now, this is an implementation that's low level, that only executes operations when they are needed and only on the portions that are strictly needed. Okay? The picture here suggested that an alternative is to transfer the whole file and to bring it back, and this is in fact full caching. It's not necessarily a bad idea, but it's different than the other one. Now it's a tremendously bad idea when you have very large files, right? For small files, it's not a bad idea at all. For example, if all the files you have in your file system are something like 10 megabytes, and for the most part, you're going to work on an independent machine and you don't care about accessing the server from multiple machines, you're much better off transferring 10 megabytes, work locally at super high speed, and then just flush everything, right? So this is essentially the mode in which some of the, for example, the version control systems work. Synchronize my copy with the server, then do a lot of local work, and then push all my copies at the same time. Has another benefit that you can actually control in what order things are merged into the main file system, right? Okay. Now, this actually provides, there is a version 3 and a version 4 for NFS, but virtually version 4 popped up about 20 years ago, so there is no version 3 anymore, right? Now, let's talk a little bit about the kind of stuff you would do on the data, because metadata means metadata manipulation. The traditional way to think about metadata manipulation is I want to organize, let's say, files into directories. So that's one way to implement metadata. It just happens that directories are, in fact, some special files that just contain entries for that metadata, but it doesn't have to be implemented this way. For example, RazorFS and XFS do not implement the metadata as a normal, regular data. They, in fact, use techniques from databases, B+trees, for example, in order to provide a much better ability to manipulate metadata. Now, that matters when, for example. So most traditional file systems crumble completely if you have too many files in a directory. Now, why is the case? Why is that the case? Because, in fact, you have now a database problem. So imagine you have 1 million files in a directory. Now, of course, you could say, who could possibly have 1 million files in the directory? Well, for example, Google, right? If you want to keep every email in a separate file, even if you do some sort of a distributed file system that's piggybacked on a normal file system, you easily end up with 1 million of those, okay? Or you're some sort of a data analyst, data scientist. Right? You run some simulation, you do some stuff, you have a for loop, and you say for 1 to 1,000, for another 1 to 1,000, go and run a query and produce a file with a result. I have my students doing this stuff all the time. Poof, 1 million files in a directory like nothing, right? So in order to have a file system that survives something like that, you in fact need to think about the problem, the metadata problem, the search problem as a database problem, okay? So then suddenly it's unacceptable to in fact do some linear scans or whatnot through the directory entries like traditional file systems do, because that's going to take forever. You really want to find stuff in milliseconds or even less than milliseconds, and then indexing, it's much more appropriate, right? So dissociating the metadata from the data turns out to be crucial and turns out to be a very big issue for distributed file systems, right? To some extent, you can think about the metadata manipulation to be closer to a DNS/search problem, and the data manipulation to be closer to just manipulating little pieces that can form big things, right? So this is really the idea behind this kind of block manipulation, which, by the way, appeared in file systems very early on. So in order to manipulate large files, we always wanted to have large files, right? I mean, think video, right? The moment video was invented, large files were right there. Actually, a particularly nasty problem in file systems throughout the ages was the fact that they limited the size of a file. It's not so much that they limited the size of the file system, which was always reasonable, but the size of one file, right? And then you have to find all kinds of tricks in the application to deal with the fact that the file system has a limitation with respect to the file size. And what's the trick? Well, the trick is to simulate a file system that doesn't have the limitation by first figuring out which file has your data and then going after the portion of the file that has the data. It's a miserable way to do it. In the middleware, you would really like the base file system to support this. But nevertheless, the data in all the file systems I know of is broken into something called blocks. Okay? Now, the size of the block, it's a very tricky matter, how big the block should be. And different applications require, in fact, different sizes. Okay? And I can give you some idea about what's going on in there. But the moment you have blocks, you have another problem, which is you need some sort of indexing on top of blocks to find the right block fast. Because very rarely you're going to have a simple access pattern to the file that is maybe start at the beginning and read everything. Okay? Now, videos sometimes are accessed in this way, sometimes, because people like to fast forward and whatnot. And here goes your nice sequential access, even in that kind of a situation, right? So what becomes crucial is not only to have a good way to manipulate large amounts of metadata, and that's arguably a data processing problem, database problem, right? But you need now to find a good way to get to the right block very fast. So the way to think about file systems, virtually all of them, is that the data part of the file is broken into sequential blocks. Okay. Now, honestly, it doesn't have to be sequential on the disk. Just in case you're doing weird stuff with the file system, for example, writing with gaps, which is allowed by all file systems. Right? So basically, this is going to be the block 1, block 2, down to whatever block, a million, let's say. Right? When you make a read request, or when you make a write request, okay, all those requests happen at the current position. So, well, this is kind of a design choice. Okay. They decided early on that they, in fact, want to at least mildly optimize for sequential read. So there are two distinct operations to be done on a file. One of them is to move the point where you want to read and write. That's the LSIC, right? And the other one is to the read or write that happens at the current position of the LSIC. Now, LSIC can take some nice values. For example, I don't remember, some of the negative values say start at the end and do something, start at the beginning and do something, all kinds of things like that, right? But instead of sending with every read or write request where to read or to write, in fact, you separate the operations. The positioning and the writing is separate. But it doesn't quite matter. The idea is the same. What you need to do is very fast find a place. I mean, not find a place. Very fast find a block that you should be either reading or writing and then do some operation on the block. This is what's happening deep inside any of these file systems. Now, this kind of linear sequential chaining of the files is necessary when you do a linear scan. But if you only have this, it's a disastrous idea if you're trying to do these fast jumps. Because you could easily have millions of such blocks. So just to give you an idea of how fast you can get to millions. Regular block size is 4 kilobytes, right? A million blocks, well, let's say the power of 2 million, which is 10 to the 20. I mean, 2 to the 20. 2 to the 20 blocks will be 4 gigs. We have files now that are 4 gigs, right? No problem. So it's very easy to end up with a lot of these blocks, which means you really need to organize the blocks themselves into an index data structure, right? Traditional file systems use all kinds of tricks to allow such blocks to be found slower or faster. You could use, though, the same tricks you use for the metadata to, in fact, have an organization on top of the blocks. And again, some sort of a B+3 implementation. But in this case, the leaves of the B+3. B+3 is like a binary tree, except it's not binary. It's wider, right? A B+3 implementation in which the leaves are actually blocks and not metadata content is, in fact, appropriate. It is known from the database community that that's a very good way to organize stuff. Now, why not binary trees and B+3s? Because B+3s are optimized for reading and writing to the disk, right? So you want to make the best out of an entire disk block. You're going to read the disk block. You want to have a wide fan out. So usually B+3s are very shallow, right, as opposed to binary trees, which are very, very deep. Binary trees are good in memory, but B+3s are good if anything is stored on the disk, right? It's a different story. I discussed about this in the database class. Okay? So organization of the disk blocks is one issue, organization of the metadata. But then you can take things a notch higher and in fact say, hey, here is an idea for a distributed file system implementation. I need blocks anyway. I'm going to do a block storage, a metadata that, I mean, some mapping between, so I'm going to have block IDs spread all over all my servers. Right? Remember this picture. All of these guys are going to have their own hard drives. And I can say, well, you know what? On these hard drives, through local file systems, because I don't want to deal with any other situation, I'm in fact going to store just the blocks. Now, obviously, you're already talking about larger blocks now, because if it's 4 kilo, just the management of the 4 kilo blocks is going to kill you. So I'm going to map blocks to files on local machines. And in fact, all I need to do is find a way. I mean, first of all, I have metadata, which I'm going to deal with separately. Then, for each actual file, I need to know which blocks sequentially, and also for some kind of an index, make up the file, and how to find such a block. So what's the machine and what's the file on the file system that, in fact, has that specific file. And this is the way you would piggyback a distributed file system on top of a local file system. Now, you do have a choice, though, right? The choice being, you don't necessarily need to piggyback on a local file system. You could access the disk at the lowest level. And to some extent, that might actually make sense, except that it doesn't give you enough flexibility when things start to fail, right? So extra levels of interaction is exactly like manipulation of pointers, allow you to move things and not tell anybody that you actually move things, right? So it's possibly worth discussing, and it's all about a trade-off. In fact, if you make the block size large enough, the trade-off suggests that it doesn't matter that you store things in a local file system versus raw on the hard drive. Okay. So let me try to draw some more pictures here, right? But you understand what the idea is? One possibility for distributed file systems would be, again, these blocks are in fact files on a local file system. Then you have some kind of a file naming technique, right? Maybe an ID, right, for the blocks. Then you need some sort of a central repository, and you say, I want to access a particular file and request a particular block from the file. And I can compute which block I want from the block size and the position where I want to position myself. And then that authority is going to say, I know who has a copy of that block. And will say, go to this machine and ask for this magic file, and the machine will give you the file. Right? That file, in fact, is the block you are looking for. That's pretty much how GFS actually works. Okay? So, well, that's actually how both GFS and HDFS work. Right? So most of the truly large-scale distributed file systems now, in fact, piggyback in this manner on top of local file systems. Then all you have is, in fact, a problem of management of all the pieces involved, either blocks that form a file or metadata, so that the files get grouped into some sort of hierarchies, or through some sort of search in order to find files. Presumably, you're going to have billions of files stored in such a file system, and each of them could get very large. I mean, most of them might be small, but a lot of them could get large. And maybe you even don't want to have a limitation on the, for example, on the file size. It's arguable that we shouldn't really have a limitation on the file size, because it's 64-bit numbers, for example, can access, I mean, 48-bit numbers can actually access 256 terabytes, right? So 64, whatever, sky's the limit. I mean, I'm sure a lot exabytes, right, with a single 64-bit number, all right? Good. But let's discuss this a little bit, because one possibility, which in fact is not used that much, which it's a reality right now, is to in fact use multiple hard drives and to put a file system on top of multiple hard drives. Okay? Now, it's kind of used, but not in the right way, by LVM, Logical Volume Manager, for example, in Linux. For example, one way to use it, which is not particularly good for performance, would be all of these hard drives. Let me draw these boxes, because in fact, everything can be viewed as some sort of a bag of bits, possibly organized into low-level blocks. By the way, the idea of blocks is really entrenched into the way disks work, right? So at the lowest level, a hard drive is accessing data in blocks and can only make available data in blocks. So in a natural way, blocks made it into the file system and made it higher up, right? That has to do with the technology that you want to put in these hard drives. You never want to access small things, because it becomes too troublesome to keep track of all of them, right? You need to manage things at a higher level. So this might be the first hard drive, and it's going to have let's say its own little blocks, but it doesn't matter whether it's little blocks or you organize them in bigger bunches at larger blocks. And I might have, I don't know, 4 of this, let's say. Now, one particular idea is the following, especially if you want high performance, very high I/O throughput. It's a must now, high I/O throughput, because we can put so many cores in a single machine. The disk was before the bottleneck. If you don't do this, then it's a disaster. I mean, you're just waiting for the hard drive to finish. So one idea, especially when you're doing reads, but you can do this with writes as well, is to, in fact, access all of these hard drives in parallel. Now, if you have a regular file system on these hard drives, and you're, in fact, going to expose each hard drive as a different file system to the application, and the application itself might be some sort of a database server or whatnot. It tries to jungle things up and try to guess where things are, and it's trying to access multiple file systems at the same time. A much better abstraction would be to, in fact, say, you know what? Why not design a file system that spans all of these guys at the same time? Now, it turns out that this technique can be used to understand how this works a little bit. So the secret for high-performance file systems is ability to read and write in parallel on multiple devices at the same time. Now, on the same device at the same time is tricky because most devices don't support something like that. Some of them do, right? Some, well, not quite. I mean, they have some queues and things, but for the most part, a low-level device will not allow simultaneous access. It might give the illusion of such simultaneous access through waiting queues, but it doesn't actually provide such simultaneous access. Okay? But on 4 hard drives, you can immediately think about, oh, yes, I could do this. By the way, the normal server configurations will easily have 5 hard drives, and you can now even buy systems that have 44 hard drive slots, especially if you're talking about the smaller ones, the 3.5, right? They have this special case in which you put the motherboard in the middle, and you simply have both in the front and in the back hard drives. Trust me, right? So this is not, I mean, most gaming machines have 4 hard drives nowadays. It's a matter of pride to say I have 4 hard drives, right? Good. If you bother to put such gaming server together. All right. And I do have an installation in the computer science department with 76 hard drives in a single machine. Why 76? Well, I mean, some of them kind of failed. I mean, it should have been some 84, but OK. All right, good. So how could you spread these blocks? What technology could you use to spread such blocks across multiple load-level devices? Now, you see, if somebody would know how these blocks are stored and where, it could actually provide the impedance mismatch. For the user, none of this exists. First of all, it's not clear at all that the blocks exist for the high-level application, and they shouldn't, because what you say is position yourself at this place and start reading and writing. Now, it turns out that the block size is kind of exposed in file systems. You can ask the operating system, what's the block size for this thing, right? Because the low-level read and write request might actually have to be aligned. So you are not allowed to misalign them at the lowest level. But libraries can actually allow misaligned accesses and just buffer a full block in memory and provide misaligned access. Okay? So somebody has to decide whether each of these blocks goes on one hard drive or another hard drive. And then you could think about reading or writing from such multiple devices at the same time. And instead of laying things out in order in this way, which essentially just will increase the capacity, move on all of them simultaneously from one end to another. Right? In this way, as long as you have large enough requests, you can take the large request, break it into pieces, one corresponding for each of the hard drives, and independently send the data to each hard drive that's going to write at the same time or read at the same time and then provide the result. It turns out that the electronics to send and receive such data are much faster than the physical act of reading or writing. So this is, in fact, a feasible solution, more than a feasible solution. Okay? Now, here is kind of the kicker. Why are we not doing this? Well, we are not doing this because, in fact, a hardware solution was proposed for something like this. I discussed much more about it in the context of databases. But in fact, if you only have something like 4 hard drives or even 10 hard drives, you can contemplate using something called RAID. Right? So RAID is a hardware or sometimes software, but implemented in the operating system technology that, in fact, makes multiple hard drives look like a single hard drive. And depending on how the information is spread around, so the RAID comes in many versions, so 0, 1, 5, 10, 50, right? They had numbers for the in-betweens, but they turned out not to be that useful. So depending on which particular version of RAID you actually use, you're, in fact, going to have the ability to put your data simultaneously on one of these hard drives and have such higher throughput access to the underlying file system, right? Yeah, but then we have machines with 44 hard drives that don't even live on the same controller, right? So then suddenly you still have the need to, in fact, have something a little bit better than RAID. So RAID has a little bit of a dark secret, namely that in software you can do better than RAID, right? And I noticed that myself. So you controlling, even at the level of the high-level application, the reading and writing to hard drives might in fact actually be much faster than the RAID controller itself. The problem is the RAID controller is to some extent trying to do too much and has electronic bottlenecks when you push it through it, right? I mean, this is a technological issue. It has nothing to do with fundamental issues. But the existing RAID controllers might have a significant problem like this. They got better over time, right? I mean, there is another problem here, namely the fact that in a very uniform way, the data is spread across all of these hard drives. Now, that is not a bad thing in itself if you have very nice read accesses in which you're just trying to read a very large thing sequentially. But if you're not reading everything and you have gaps into your reading, this can actually create problems. Because if the way the gaps are aligned, the strides are aligned with the hard drives, you might lead from far fewer hard drives. So there are some situations in which you might want to have a more randomized access to how things are laid out on the hard drive and not a uniform access like the RAID system has. Okay? Now, a particular thing that you might be interested in is, for example, to provide such very fast access over the 76 hard drives, we in fact implemented using the C++ version of the actor model in less than 300 lines of code. Well, it's far less than that in the end, right? So what we ended up doing is something, it's extremely high performance because it depends on none of the fancy features in the operating system. But what you need is an actor at the top that's a disk array. And this guy provides the illusion that the space is in fact flat, like this. So whoever sits on top has to do its own metadata management to figure out how to lay things down in something flat like this. But the disk array provides the flat illusion in a very large space, but in fact is going to use HDFred actors to control each physical device. Okay. And then you can do all kinds of fancy stuff if you're doing this. So you can send a large request to the disk array. The disk array takes the collection of many pieces that need to be read as part of this request and simply chops it into pieces, one for each of the HDFred, sends messages literally to all of these HDFreds. They do their own stuff, right? And they don't even bother to talk to the disk array. What you can do is say, you know what, the entire request required 55 pieces to be put together. What you can have is something that I call a distributed counter. So you can have a distributed counter, and only the last guy, only the guy that makes the counter 0, in fact, has to send a message to the disk array. So you can even cut down on the number of messages as long as you have this other gizmo called distributed counter. Or you could, in fact, because the requests are quite large, possibly, you could, in fact, send a message every time you read it and you send a message, and the disk array is going to do the counting. And when all the 55 pieces are there, then you're good, and you can push up the message saying, yeah, whatever you want me to write as part of this request is done. Right? The actors provide tremendous flexibility in here. You can have multiple simultaneous requests going down. Now, of course, at the level of the HDFred, there's no point in doing simultaneous requests, okay, because you're accessing a physical device which can't do things in parallel, right? But you can have just the normal message queues waiting. The normal message queues that these guys have will allow, in fact, requests to pile up and these guys to be busy almost all the time. So if you're careful and you do things a little bit in advance, right, you're going to keep these guys busy at full speed, and you're going to read from these hard drives at the full speed of whatever your bandwidth on the I/O bus will actually allow, right? And this is how we manage, for example, to get to speeds that are unheard of, either with RAID cards or with normal file systems, right? So to give you an idea, right now from the disk array, we read at about 3 gigabytes per second. There's no hard drive that can do 3 gigabytes per second. Right? We can read at 3 gigabytes per second and sustain speeds if you read everything sequential for whatever the storage is. I think the storage reaches now something like 100 terabytes. So you can read 100 terabytes at 3 gigabytes per second sustained speed. Right? In fact, if you look at all the hard drives, you can see it's almost like a Christmas tree. There's all the lights coming up at the same time. And all of it with relatively simple technology. So the message here is the following. Stuff you learn as part of this class, for example, Scala actors, could be used in a very straightforward way to, in fact, do this extremely high performance reading from the disk, as long as you design these little actors that will just use a simple API. This is really the idea in distributed file systems as well. Local file systems are not bad. They just don't provide all the facilities you want. So if you install the right local file system, you can actually have very good performance, right? So why not, in fact, use the very solid, very good implementation of the local file system and build the so-called distributed file system on top of it as some sort of an abstraction? As long as you figure out who has your part and you have a way to go get it and bring it back, you're good, and you don't need to redesign everything from scratch. So another lesson here is when you need to build some kind of a fancy gizmo, consider very seriously reusing existing parts to do various things, to just reassemble it in a different way, right? Don't necessarily be very concerned about, okay, but maybe I'm going to lose a little bit of performance here and there. For example, here, you can be very concerned that there are too many parties involved, one, and two, potentially you could do much better at the lowest level. It turns out that for many reasons, you want this block size to be quite large. So any idea how large these block sizes are? So the normal file system has 4 kilo blocks. Let's throw some wild guesses what the HDFS or GFS likes for a block size.
4 megs?
More like 64 megs. All right? So since the block sizes are so large in these distributed file systems, right? Any kind of concern about, I mean, they are selected to be so large so that you can do something very relaxed on top, right? Any consideration about who did what and how things got glued and how fast in memory you could look up on an index are basically irrelevant. Transporting 64 megabytes in itself is where the time is spent, right? So if your application can support such a trade-off with very large block sizes, you in fact can mask any kind of presumed inefficiencies in how the file system is implemented. The secret with such a file system, especially at the level of the metadata and the organization of the blocks, is to have a very sturdy implementation, not to lose these blocks, because you lose basically storage in time, or not to mess up the metadata, because you can easily mess up an enormous number of applications you build actually on top of it, right? So more and more what we see is a trade-off in which you prefer to have a solution that potentially is not such high performance, mask it through some other, changing some other characteristic, but prefer to be on the safer side. Rather than hack all of that stuff at a very low level, all of this metadata management can be done at a reasonably high level, and to a large extent you can even use a database to manage the metadata. So for example, what we've done in our own implementation of a database system to provide access to extremely large relations, the relations can be as large as the sum of all the hard drives, right? And to provide metadata is in fact to lay things down without a file system, because I don't really see the benefit of a file system for this kind of blocks, but to have, in fact, a database managing the metadata, right? So, for example, when you want to access a relation, which is basically just a table, what you have to figure out are things like, OK, which columns do I need? OK, for every column, and for this current position, as I'm reading part of the relation, which are the blocks that, so you keep on looking in the metadata and you say, which are the blocks that actually correspond to this? So not only that you have the high-level organization, the metadata organization, this is the higher level part in the database, but you have the lower level, namely where things are laid out on the disk. Now, the only thing that you don't have in the database is which of these subparts contains the blocks. Only the disk array knows how the data is shuffled on multiple hard drives, right? Why? You still want to have a, I mean, you're better off with a formula here, some sort of hash, in fact. You're better off with a hash here than, in fact, allocate them independently. You're not going to save much if you do that, right? So the flat view of the world, any information above that is managed in an actual database, and we use SQLite database, which, by the way, is perfect for this kind of purposes. And the SQLite can easily deal with millions of moving pieces and whatnot. It's not going to be a big problem. And everything below that is going to be through this disk array. Now, in case you're wondering, this hash function that we're using here, and this is the level of manipulation you can actually do. The hash function we use there is designed so that if I don't read all the columns, because the data is stored by columns on the disk, if I don't read all the columns, I still have pretty good access to these hard drives. The problem is, if somehow you have 4 columns and 4 hard drives and you need only 2 of them, it might be the case that 2 columns end up on 2 hard drives and you don't get the full bandwidth. But with that hash function, you can actually all the time change where things are laid out, right? So you can have this semi-random layout on the disk in which things look random, but in fact they are just a nice deterministic function. You simply change the manner in which you lay them out on the disk. So maybe the relations, right? In one of the slices, a column is stored here, but in another slice, the column is going to be stored here, or things like that. Now, you see, it doesn't even matter what you do in there. Once you do this kind of a very nice design with actors, you know that you want to manipulate this. You simply go and pick a number of choices there and see which one is better, and just run a bunch of benchmarks and say, hey, this is better than another one. One possibility being the round robin used by something like the rate controller, right? But you, in fact, can do much better than that, right? Now, any kind of access pattern that's very uniform could actually interfere with physical devices. And you're usually much better off if you break the symmetry in the access pattern. Because you simply can produce these ups and downs and ups and downs, and those will produce some sort of a big waves that actually form in the request, and that will actually kill the performance, right? So it's exactly like physical devices. If you get the right frequency, they start to vibrate. The same thing can actually happen with the entire disk array. You get in the wrong spot with that kind of access pattern that goes regularly up and down and up and down. And in fact, everybody's just trampling over each other. It's exactly the same situation as, for example, the wireless access channel, in which you have to do random backups to try to get the channel, because literally everybody will start to get it try to get it at the same time. All you need is to massage this little thing here. So what I'm trying to say is, once you don't insist on very low-level implementations that are very uniform like this, and you allow high-level implementations on portions. The only thing you care about is how fast you can read and write from the hard drive. Can you access the low-level API or not, really? Beyond that, what you do in these actors and higher up can be written in any high-level language. For example, even for what we write, it's designed for cuteness and maintainability and not for performance. The only thing I need is the fact that once I say read this block from the hard drive, I use the right API at the level of the operating system, so there's nothing in the way, and it's going to read it as fast as possible, right? This has more to do with aligning, for example, in the right way requests and other gimmicks, right, which can be done as well from Scala, rather than any kind of very tight code implementation here. It's more about the parameters that you send to the low-level request than anything else, in fact, okay? So this is really, for example, the way I do things and the way I wanted to think about that. Now, to a large extent, I don't know anybody doing this, but a particularly interesting thing would be to even implement a distributed file system using Scala actors, in which actors will deal with the metadata and with this, and maybe access the database to deal with some of these things. But finding who has what and doing some remote messages, for example, in Akka, could be a real possibility to, in fact, have a very neat implementation of a distributed file system, right? And maybe that makes for a kind of interesting project for future generations that take this class, just to change things a little bit. Okay. Now, there are many other possibilities here. One of them is to, in fact, have redundancy, even on multiple hard drives. So as long as I decide which blocks will have the same copy, when I make a write request, again, this guy can do anything it wants. So when this guy sees a write request, he can say, you know what? I don't want to write on a single hard drive. Let's write on 2 hard drives, the different locations. This guy is managing everything, so simply takes every write request and splits it and sends it to 2 guys. These guys don't even care what is it that they are doing. The boss pre-choose all the food for them, and everything, it's nice. The other benefit is, if you do such a scheme, if the disk array, instead of just waiting for the hard drive threads to actually do something, or the hard drive actors, it can actually start to time things and see if anybody is late with a request, and in fact decide, okay, something is wrong with this hard drive thread, or maybe that portion of the data for the hard drive thread. Why don't I go and access one of the copies to get the job done? Now, this is a technique that can not only be used here, but is used all the time in a big way in any big distributed file system. So all of them will provide a tunable level of redundancy. So you can say do 3-way replication. That means every piece of data is stored in 3 different places. So somebody must know where the 3 different places are, and in fact switch from one to another, right? This in fact allows you also to do some form of load balancing. So if all of the 3 copies are healthy, you simply switch between which ones serve different requests. But also allows you to mask failures, which is what distributed systems are all about. I argued from the beginning of the class. Namely, the boss determines that something is wrong with one of the copies, either at this request or in general, and simply sends request to another copy. So you have many options, both through the manipulation of the metadata or through the manipulation of, if you want, the metadata on top of how the blocks are organized to provide such redundancy, right? But in the end, the way these blocks are stored is usually very simple. And most file systems would not actually lay them out on the disk at the lowest level. They will piggyback on top of the normal file system. Now, that's usually not a big problem, right? Because especially some of the file systems are designed for performance. XFS, for example, is designed for just simply raw performance, so it has a very, very good throughput. It's very lean, it has very little overhead, right? Now, why we lay things out directly on the disk, I don't even remember, but at least I don't have to manage files. I just do everything through a database, right? So literally, even a very good implementation of a distributed file system might require some database, for example, SQLite. SQLite actually runs, by the way, it's an embeddable database. It runs together with the rest of the program. It's not a separate server. Some sort of a database to massage the large amount of metadata, right? And then some sort of actors to coordinate access in parallel to multiple hard drives. And you can actually get an extremely high-performance system with very small footprint, 1,000 lines of code or less. Right? That can actually be both sturdy and high throughput for specific situations. Right? In this situation, what we want is these enormous relations that are read in a sequential manner, but only certain slices from them, certain columns. So we designed something for that specific purpose. Okay? Now, most of the time, you're going to be in a situation in which you, in fact, have to decide whether to use a distributed file system or something else. And distributed file systems could be the answer to a lot of your problems. Right? Then your only worry is from the middleware to write against the distributed file system API, which is very much like a normal file system API. Now, I do want to give you a little bit of a warning / heads up with respect to this. Some distributed file systems are implementing like NFS deep into the implementation of the file systems in general and access through the virtual file system. Some of them require higher level API. For example, HDFS has a little bit of some sort of programs that can be used from command line to access it, but for the most part is just Java API to access it. GFS is more mysterious. Maybe this slide tells us what it does. 1 second. I'm going to come back to this. Where is the Google one? Well, as you can guess, are in many different implementations of these things, and all of them are slightly different, better for this and better for that. Okay, F5. So I think they have some slides, but not in the order I like. Do we see any Google slides here, GFS? No, it's just the global name file space. Okay. It doesn't matter that much. So GFS is a little bit mysterious because Google doesn't like to talk about details. Usually, no pun intended for Google people that ever watch this, but basically, Google builds internal tools. Sometimes they let stuff go out there. I think they eventually open source the GFS, right? But it was designed for internal using initially. And I think the initial API was just some sort of a C++ interface. And then Hadoop did HDFS, and that was just Java. Some of them take the trouble to put it into the virtual file system. Now, of course, this is now big business, distributed file systems, right? Because this is what these new companies, right, Dropbox and Box and other kinds of boxes are providing. This is what the cloud storage is all about. Cloud storage is really distributed file systems, okay? So it's a new hat for something that's very old. A lot of the things discussed on these slides are, in fact, 30 years old. I mean, file systems appeared 50 years ago. And the moment they had free machines that could talk through some sort of a network, they immediately thought, hey, could we make the files move in between these machines? And that's when distributed file systems were, in fact, born. Okay? And they had cloud storage then. They just didn't know it. They had to coin the term only in 2005 or whatever. Right? So cloud storage is really distributed file system, to a large extent. Cloud non-storage might or might not be piggybacked on a distributed file system, but cloud storage really is, right? So in fact, every time you either backup or you actually keep your files in the cloud, you're in fact using a distributed file system, right? Dropbox has all kinds of cute tools and cute techniques to provide the distributed file system. By the way, you might not even be aware, but things are much more layered than you think they are. Right? So in particular, for example, that especially the Dropbox people are very clever. Okay? So how do you think Dropbox stores the raw files in the Dropbox file system? Right. So you would think that they would actually take the trouble and have their own servers and do this stuff and organize things on the disk. But they're actually much cleverer. What they do is they use Amazon's as free storage instead of doing their own. So they're completely just middlemen and protocol men. Okay? When you make a request to Dropbox, Dropbox does some cleverness to cut down on how many requests they do to Amazon as free because they have to pay money for every data transfer and for storage. And then they simply ask Amazon to do the hard work, namely to store it in the local file system. So you, in fact, use two file systems. You use the Dropbox's interface for a distributed file system, and Amazon as free is actually lower level distributed file system, right? Now that's one way to do things, right? And why not? Makes you wonder why not use S3 in the first place, because in fact you have access to possibly lower prices. It's not even clear if it's actually cheaper, right? So it's kind of the retail versus bulk price for that. So Dropbox adds though very interesting features on top of it, right? So S3 does not come with any sophisticated high-level interface. It's like a bare-bone, low-level distributed file system, just to read files, do things like that. And Dropbox has all the super fancy features, fancy clients with notification and cutting down on the communication, doing this between files. So they also do version control on stuff and so on. None of that is present in the underlying layer. But what I'm trying to say is even the big guys are building on top of existing facilities because it's really not worth going too deep. So to a large extent, I mean, this was a more clear-cut situation for us, but to a large extent, what you should do is, in fact, at least use local file systems, if nothing else. And then just maybe find the one that's sturdier. XFS is a good choice, for example, right? I don't know what Box and the other guys are doing. But the value added, apparently, it's all worth it, right? And from the point of view of the user, it's all some sort of a high-level facility, right? Now, there are many, many ways to implement these file systems. And to a large extent, every vendor will consider different ways to balance all the requirements and provide a different version of all of these file systems. Now, as long as the dirty work is done by somebody else, right, a local file system or maybe a lower level, not so sophisticated distributed file system, you can actually try all kinds of fancy stuff on top, and you might actually have pretty fast development on that, right? If it's fast enough to develop something like this, and by the way, for example, mine, because I used the SQLite database and raw access to the hard drive and so on, it was one person working for a week, and I got a nice layout for the super high performance read and write, nice layout for for my database, right? It's kind of, it almost sounds silly, right? In the implementation of a database, you use another database to do the dirty work inside, but that's what the file system people are doing, right? I mean, why not? Because the hard part is to get the little stuff going right, okay? And XFS is actually so good, you can have a million files in a directory, and it does a very good job. So you don't even have to sweat too much this metadata stuff, even from the point of view of accessing and finding such files. Okay? Now, these are examples, for example, of possible implementations. And specifics don't matter so much. The high-level ideas do, though. Right? So cluster-based distributed file system in which you have a master, and then you have all of these parts. The GFS is like this. So it's a global coordinator kind of solution. GFS and HDFS, they all use this. Now, here is the strange thing. The distributed file system community, the distributed systems community, the research community, is completely against the idea that you have centralized solutions. Okay? It's just a big no-no. If you're trying to publish a paper that has a big server at the middle, they immediately reject the paper and say, fatal flaw, single point of failure. But the fact of the matter is, that master, or maybe a little bit of a redundant master, it's used successfully for many years on extremely large scales by both Google and Yahoo with large Hadoop installations. And all of those disasters that the distributed systems community is talking about are really not necessarily there, right? a redundant master might be a good enough solution for all of these things. And in practice, it turns out not to be as big of a nuisance as painted by the distributed systems community, right? So they transform a potential bad into a true fundamental evil, and they're completely against it when it might actually work. If you have a master that coordinates what all the pieces do, the system is much simpler. But the trouble is, as you have seen, when you're trying to do this, for example, you can imagine that, hey, why not use peer-to-peer systems? And there is actually Ivy. It's a peer-to-peer system. Distributed system, it's a distributed system implemented on top of the peer-to-peer system. Now this comes from Berkeley, where CORD was proposed and these distributed hash ideas were proposed. And again, this looks very nice and dandy and looks very interesting, right? But nobody's really using it, and that's the problem, right? From the point of view of let's say, practical impact. So if you ask people what do they have in industry as their implementation of distributed file system, they'll tell you it's something like Hadoop or GFS. Or maybe some other ones. That Andrew file system was, an example, a much older one that did distributed file systems with the same kind of ideas, right? They're not going to say we use Ivy. But it's nevertheless an interesting kind of exercise. So on top of, you implemented CAN. CORD is similar to it, right? On top of, or was it project 2? Or 3? Project 3. On top of your project 3, you can actually imagine that you implement a full-fledged file system in which you have to, with separate requests, look for metadata, and then again, the metadata might be distributed and stored on multiple nodes. And then once you figure out what the metadata is and say, I need this block and this block and this block, and you chase them down as if they were independent files. So the idea in the original paper was to store entire files using, and just communicate through a framework like CAN, right, or CORD. But you could say, no, let's not do files, let's do blocks. The blocks are sizable anyway in such a system, right? So for example, 64 megs is much larger than most of the files out there anyway, right? And that will in fact add the ability to have this kind of implementation. Is called symmetric architecture for the file system, right? So then every metadata request requires some sort of jumping around to find who might actually have the metadata information about the file, and every block request would follow the same kind of a path. And they could go to very different places, right? Now, this can, in fact, can be used for other reasons, right? So some other reasons can be, if you, in fact, use encrypted blocks and various sites that host the encrypted blocks cannot decrypt them, so you need to access the decryption keys for a completely different pathway than accessing the data. In fact, you have something usually referred to as plausible deniability. You can't tell me that I infringed whatever copyright because I was keeping an encrypted file and I have no idea what's in the encrypted file, and there are legitimate uses for the encrypted file. So you have no way to prove that what I had was, in fact, a bad file, right? It's as if you would trade drugs but also have newspapers and letters in boxes, and you don't know if the box is locked. You have no way to tell if you have a nasty stuff in the box or non-nasty stuff. You're just routing the boxes around. Well, maybe not such a good parallel, but right? Now, how hard would something like this fly is not clear. Okay, they usually get them for much smaller stuff than the files themselves, but that is a possibility. Now, and this is probably worth talking about in general. Whenever you're talking about such large file systems, right, you must contemplate at least the possibility that you're going to encrypt some of them. So this is particularly important when it comes to the cloud. By the way, the fact that it's very convenient on your iPhone or Android phone or on your desktop to put all of these files and stuff around doesn't mean you should disregard the security. So here is a fundamental question. I mean, maybe this is a life lesson more than a distributed systems lesson, but it rides on distributed systems and security at the same time. The basic principle should be don't trust anybody with your files. You really shouldn't. I mean, including things like credit card numbers and so on. I mean, you have, for example, personal information that you have to keep. How do you keep it? Now, the cloud storage has a tremendous benefit. It has an extremely high uptime, and they have a big incentive to keep it there for a long time. And for the most part, now it's free, right? On the other hand, if I store my personal stuff, at least the guys that hold my files could, in fact, read them. But potentially, you can read the communication between data centers. I'm not sure if you pay attention to news, but Yahoo announced that they are going to encrypt the communication between data centers, Why? Because people were listening on the communication between data centers. So it doesn't matter that you have access control. It's irrelevant if you communicate between data centers and you say send the data in the clear. I mean, what's the point? So how would you still use the convenience of a cloud storage, but the security of, the proper security? Now, the fact that you have a password to log in into their system means nothing. Okay, really nothing. I mean, the password might be used for authentication, but probably the traffic itself is not going to be guaranteed to be encrypted in the right way. Even if the traffic is encrypted, the hard drives are not encrypted, right? And Google employees can actually steal your data, say, or other people can eavesdrop, right? Well, it turns out that there is a cute solution for this, and it's only a minor nuisance, okay? Namely, encrypted file systems in a file. So you see, let me go back to the picture. I want you to understand that the moment you open the door for a certain kind of abstraction, it can take a life of its own and provide very surprising things. So here is something possible in any operating system that has a virtual file system. It's possible to, in fact, create a full file system in one of the files here. It's called the loopback device. Okay? So you can basically, because there is really no way to tell the difference between a file and a device. The way devices are exposed is through something that looks like files. Right? Now, you could check some nuts and bolts on it, but you, in fact, have to struggle to even tell the difference what's a file and what's a device. I mean, just to give you an example, but you can tell only because I give them nice names through convention, but otherwise you would not be able to tell them. /dev/sda1, right? This is, or even better, /dev/sda. This is, in fact, the first hard drive, okay? But /home/blah, this might be some file, but how do you know? So for example, both are names. How does the operating system know which is a device and which is a file? Well, it turns out that it has very nuts and bolts kinds of stuff right in there, and has enough in the metadata to allow it to say this is in fact a very special file and refers to a physical device. And you can do that by essentially mapping something called a major and a minor number into something that the operating system understands deep inside. But the bottom line is the following. Most tools that will allow you to create file systems will, first of all, they don't need to, and they won't, make the difference between this and this. So you can create a file system into a file. You simply treat the file as a raw device itself. So when the file system says, I want to write this block, that corresponds to a certain position in the file, and somebody else goes another level down or another level down or whatever it is doing to get to the raw device. By the way, even writing on a hard drive is a complete illusion. You have no idea necessarily how that maps into physical bits on the disk, and it's not simple anymore. They do all kinds of tricks which are actually proprietary. They're secrets, industrial secrets, not even patented, right? So there's no simple thing anymore. It's anyway a virtual. I mentioned this before, until you get to some sort of a physical representation, which can be only remotely related to what is it that you are doing at the high level. Now, the virtual file system will allow you to do that. You create a file system in the local file system, and you can actually mount it. And this is one of the big ideas that I want to show you on the slides. Now, through this mounting, right, you can, in fact, have file systems in a file, and as long as those file systems have encryption support, and we can talk about how that can actually be supported, you can, in fact, then, in a single file, have an extremely secure implementation of a full-fledged file system. Why do we need file systems? Because they are a convenient way to organize data. If a file system lives inside the file, I can just take that file, which now can be manipulated by a lower-level file system or any file system, then be moved around. So one particular solution, and we can talk about the mounting points and so on and how that can be hooked up, would be to create a file system in a file, and the file is stored in the cloud. This way, it's almost like a security protocol, right? You remember those complicated security protocols that had elements in them to make sure that you resist certain attacks? The attack we are talking about here is somebody can access your files and read the content. But if you have an encrypted file system into a file, and that file is moved into the cloud, then you say, OK, fine, whatever, but what you're getting is a nonsensical bunch of bits unless you have the right key. And this is where things like AES-256 and whatnot come into play, right? Now, of course, it might be a little bit less efficient. It's related to the question you had. But it's much better security, right? So, I mean, this is a personal advice. If you need to keep credit card information or whatnot, create one of these encrypted file systems in a file. For example, TrueCrypt will do this, and simply take that file and put it on the cloud storage. Actually, hey, for what it's worth, put it on 3 different cloud storages so that if one of them is unavailable, the other one is available. As long as you don't change this too often, you're going to be perfectly fine, right? This does open up other interesting questions, right? The difference between client-side and server-side, for example, encryption and decryption. Client-side encryption has the tremendous benefit that only the server cannot manipulate, read in particular in a clear way the client's data. So this is essentially a situation in which the server gets the encrypted version and has no way to decrypt. Right? That can actually be tied up with those ideas related to using public key cryptography for and some other kind of encryption on the client side. Okay. All right. So let's see a little bit the story about the mounting points. I had something similar a long time back. I want to remind you. Now, these are basically just various protocols that can piggyback on top of remote procedure calls or some kind of message passing or actors discussing through messages or whatnot. And there are many such things implemented in the literature. Some of them are in wild use, some of them are not. I mean, for example, Coda was reasonably popular until Google started buying machines by the millions and implementing their own file system. I mean, once you have big enough muscles, you can do whatever you want, including say, you know what, we are going to create our own file system, and we are going to dwarf anybody else who uses distributed file systems in terms of number of people that use it and the volume of the data that's used. So suddenly, something like Coda can go from the primary distributed file systems to nobody knows about it because essentially everybody uses HDFS or GFS. Right. So I mean, your fortunes can turn one way or another very fast in this space. Right. So the idea of, well, I mean, metadata about files, it's all about naming and it's all about finding what you want. Right. And a big question in general is what facilities you should have to allow people to find things. Because arguably a directory structure is about organizing the metadata in such a way that you could find it later. Easier, whatever easier means. I mean, I personally find directories annoying. First of all, I never remember where I put something, right? I might have had the right inspiration to name the directory or subdirectories or whatever in some way that suggests what it is, but it takes me too long. What I personally like is ability to search. If I could, for example, most of the time you can remember fragments from the file name much easier than in what directory it is. And the fact that the files are not available in a single place is annoying. If I could have all the million files or whatever in a single place and just do an ls with stars in it, that's a faster way to maybe find the file. Okay. And you might even decide in certain file systems not to provide a directory structure at all, to just provide search facilities. Right? For example, you could even think about pictures. Right? Pictures can be organized into something like collections or whatnot you want to call them. But what's much more often employed when you need to see such pictures, and pictures are, you can think of them as files into some sort of a file system, distributed file system. It's look for pictures based on tags or some other things that seem to be more useful than collections themselves, right? Anyway, the way, okay, so there is something here. I mentioned this before, but let me remind you. This virtual file system here, it's a little bit mysterious because virtual file system, it's an API, but any virtual has to correspond to a concrete something at some point. And the question is, how do you know which concrete implementation of the file system to use to hook it up into the universal interface, which is the virtual file system? So the virtual file system is the API, and the specific implementation matches perfectly the API. But okay, for example, you can have multiple file systems on any operating system, and all of them have multiple such file systems. Which one do you use? I mean, there is first a big question, which is the file system that is the big main file system? But what seems to be much more useful, and that's clearly the case in the case of NFS, is you want to have both a local file system and a distributed file system at the same time. Or you might want to have multiple local file systems, just because you have multiple hard drives or safety or whatever reasons you have. So in order to provide multiple file systems at the same time, you must have some sort of abstract paradigm that allows you to do this. And there are basically now two prominent schools of thought. Okay? One of them is the Unix way, in which there is a single global file system, and you have something called mounting points. So mounting points are special files that are not files at all. It's points where you switch from one file system implementation to another file system implementation, right? So essentially, if you go through the mounting point, you're switching which functions are hooked up in the virtual file system implementation. So you might start with an X3 file system, which is the global file system in a Linux system, but then going through a certain mounting point to cross over to an NFS client, which now does this much more complicated thing. Or if you do this, for example, loopback device with TrueCrypt or whatnot, to cross over into an encrypted file system, right? Now, this is very convenient, and it will allow you seamless integration and switch between such file systems for the mounting points. And this is the idea with the mounting point implementation. Right? So for example, this would be mounting points, in which you have the normal file system, but this is a mounting point, so the moment you cross through it, you in fact, this corresponds to something else that happens on the server. So the virtual file system illusion with distributed file system implementation, it's created in this one. It still looks like a local file system to you. The major benefit is to all the applications and to the user, the mounting, the possibility to mount, will allow you to access, and the uniform interface will allow you to access very different resources in exactly the same way, and not even know when you're in one versus the other unless you have the right tools to inquire the operating system about that. Okay? Then you can have also very fancy features like auto-mounting, for example. Auto-mounting is the act of mapping a certain file system into a certain place, but only when it's accessed. This is very convenient for servers. For example, this is done all the time by the CISE sysadmins. You might actually store homes on 20, 30 different hard drives. You don't want to have all of those things mounted all the time. You're going to mount them only when anybody accesses them. And then you mount them, and then if they are not used for whatever number of minutes, you unmount them. This preserves resources in the server, because it's exactly like networking. The moment you mount something, you dedicate resources to watch the traffic, the dedicated whatever program or daemon that actually has to watch all that stuff and so on and so forth. So there's a big incentive to not keep them alive all the time. Okay? Right. So let's go a little bit back to this idea that you're going to use encryption, and especially client-side encryption. Client-side encryption, again, it's extremely powerful because only the client can decrypt, presumably. You have to break the encryption to do anything else, which means all of this cloud stuff makes sense, right? So for example, a particular use of this would be, I can take, for a company, right, I can take the data for the company and not be too worried that I store it in the cloud. That can be very secret documents and whatnot. And in fact, put it without worries on their servers because it's encrypted. I still need to bring it on portions or completely on this specific hard drive to actually provide the decryption. Now, think even in terms of what a good implementation for an encrypted file system would be. So think TrueCrypt, for example. It will implement in a file a full-fledged file system that's actually encrypted. But if you're a designer of a file system like TrueCrypt, you know for sure that data is still accessed in blocks. So you want to make sure that the blocks in the file system, your file system, are aligned with the blocks in which the underlying stuff is implemented. Right? And if you do so, and if you do block-level encryption, then you don't, in fact, have to move the entire content of the underlying file on the local machine to be able to just open it up and decrypt it. You can, if you do block-level encryption, whenever a request is done into something like TrueCrypt, right? So the situation is really TrueCrypt as a file system sits on top of a file that's implemented in another file system or distributed file system for that matter, right? It can live completely in the cloud. The file, it's in the cloud, so for example, the file, it's a Dropbox file, right? So if the block in the TrueCrypt file system corresponds to, in fact, a block in the file and possibly corresponds to a block in the distributed file system implementation, actually the performance and the way the decryption can work and so on, all of these things are going to work nicely together, because you don't, in fact, need to move the entire file locally here to be able to put the file system on top of it. It's all basically just some sort of a abstraction, some sort of illusion. So in TrueCrypt, you're going to say, I want to read this file, which means you have to access metadata, so that will involve reading or writing, reading some parts of the underlying file, which hopefully everything is encrypted, right? And then access some content of the file. But accessing some content of the file, if it's done carefully, means only read this block, which means only this block from the file, which means potentially only one block in the underlying storage for the distributed file system, right? So then you only read what you need, or you only write what you need, and not everything. And that's a big advantage, because otherwise, if you have, for example, you can say, hey, encrypt my entire home, which can be several gigabytes. If you have to transport them all the time, that will be a disaster. Okay? Now, it's not only TrueCrypt that does this. I mean, most operating systems will now offer a facility to have something called disk-level encryption. So the idea is basically, why not, and it has to be done block by block. Now blocks are crucial. Why not do this for everything on the raw hard drive? So that basically means at the level of the raw device, data is split into blocks. Each of these blocks is encrypted, say, with AES-256 independently with the secret key. Now, you can make sure that the secret key never leaves on the server at all until you, in fact, put the password. The password is translated into some sort of a key, and then the key is used to even start reading the file system. It's going to be impossible to do anything with the low-level files. By the way, a nice way to protect against information lost on laptops. I mean, we have laptops, right, all the time, and I already managed to lose a laptop, right? So I'm kind of on the other side of the fence. If you have full disk encryption and absolutely everything is encrypted on the disk, then you don't have to worry about, did I have some important data, student grades and whatnot on the laptop. It's like, yeah, whatever, because I know that unless I booted the machine with the secret password, right, it's going to be impossible for anybody to make anything out of that file system. And Linux and Windows and so on, they do, and Mac OS X, they do support full disk encryption, but with a big warning there, and the big warning is, don't lose the key because there is no way to recover anything. Okay, so that's the big downside on all of these things. It's the same thing with TrueCrypt, right? It's not like the good old times in which if you lost the password, you can go ask the admin what the password is. If you only do authentication, that's a possibility, or there is a way to reset the password, right? Cryptography is much stronger, but there is no password recovery. Actually, the Mac OS X, I don't know if you ever play with it, it strongly encourages you to set up both passwords for the full disk encryption and a master password, so you have two passwords. The master password, maybe you keep it in a vault or whatever, and you don't use it too often. So then what do? They keep a special block at the beginning in which they take the actual key used to encrypt the hard drive, encrypt it with the master password. But of course, you need to do this trust propagation, so you need to know the master password. Normally, you wouldn't access that because you know the normal password, but if you lose it, maybe the master password would work. That's very good, for example, when you have sysadmins installing software on machines of various users, in which both the user and the sysadmin has access. I mean, has a way to get access to the file system, right? And that's yet another security protocol in there, right? So you might gather encryption keys into some sort of a bigger repository and use some sort of a master key. You don't even need to use a master key, actually. You can use public key cryptography. And that's actually a very convenient way to do it, because once you do it, you can't undo it. So what you could do, and that's a really safe way to do it, right? So a truly, truly safe way to do it would be, at the level of your entire organization, you come up with a private public key pair. You take the public key and you, in fact, hardwire it on all the machines. Only the software would allow you to do this. Every time somebody sets a password for the full disk encryption, that password gets encrypted with the public key and stored in the clear on the hard drive. Now, only the guys that have access to the private key corresponding to the public key can actually undo this process. And then you have a way to recover things, but at the same time, it's secure, right? Now, unfortunately, it's rumored that occasionally when Apple implements some of the security protocols, they make sure that they have access to the key through some tricks like this public key cryptography and encrypted with the public key, right? And that's not very good, because that essentially means that Apple will, in fact, be able to read your file system. Now, if that's good or is bad, it's a different kind of question. but it's there, right? That's one reason, by the way, to use Linux, because all the code for Linux is out in the open, and if anything like that would happen, people would have noticed. Right? And TrueCrypt is the most paranoid of them all. Right? It's out there. I mean, truly paranoid. Right? It's possibly, because I don't want to talk too much more about the distributed file systems, right? It's mainly this idea that I wanted to get. So just to give you an idea of what you could do, in fact, when it comes to security protocols, you could, in fact, use a two-factor authentication all the time, even when you use encryption, in the sense that you can say, you know what, instead of typing a password to unlock my file system, what I can do is, again, use this public key cryptography, in which you generate a public key and a private key, right? The information on the hard drive is encrypted with the public key and is stored a very complicated password than AES-256, because it's very high performance. It's actually used to encrypt the entire hard drive. And you get the private key, and you encrypt that with the password, and you put it on a USB stick. Now, essentially, access to the machine, because I don't know if you've seen those private passwords, right? We manipulated some of them. If you put them on a screen, they are only about 20 lines or something. Right? It's enormous. It's impossible to remember anything like that. I mean, even for people that have special skills. Okay? So if you do that, then essentially you need physical access to that USB stick that, in fact, has this encrypted private password, knowledge of what the private password is, and then you can use AES-256 to, in fact, encrypt the private key. Right? So you need both a password and a physical device to unlock something. You're already getting to the level of the mechanisms that are used to secure nuclear weapons, right? When you have two-factor, three-factor authentication. And people are, by the way, now seriously considering there is a big hullabaloo on the web because of the NSA debacle, right? And people are thinking to seriously implement two-key cryptography, in which you need two parties to put together a key to be able to unlock something, right? And if you do that, you essentially have to acquire both keys at the same time. Then already the cryptography literature is full of protocols in which that can be used for group communication, in which you can say, unless I have 3 parts of a key. So if you have 100 participants, at least 3 of them might have their own key to be able to form the key that unlocks the door. And no individual key or 2 keys can actually be used. These are very weird schemes, right? And it's not something that you want to design on your own, but they do exist out there. So it's actually known for many years how to have a minimum number of keys to be able to patch together something that actually unlocks the big thing. Okay? And there are very carefully designed security protocols to build such things as well and to manipulate such things. Okay? So hopefully what you get out of this is security is very important, has to be everywhere, can be mixed up with file systems and whatnot, right? Now, for example, metadata might or might not need to be protected, but one way to protect it is to actually dissociate extra information in the metadata and to put only some sort of IDs that mean nothing, right? Because you still need to manipulate it, and then the blocks can actually be encrypted at the lowest level themselves. Now, block security is not as good as stream security, but it's still very, very good, and nobody figured out how to break these blocks as well, right? If the blocks are very small, for example, just 32 bytes, then it's a disaster. If they are already something like 4 kilobytes, then no known reasonable way to break the security is known for if you deploy something like AES-256, even if you repeat the key. And you could use other things. For example, you could combine the key with the block ID to, in fact, derive a key for what the block is, or things like that actually strengthen the cryptographic system. Okay? So let's stop here. It looks like you are in full swing with a new project. And remember, I just want to see cool stuff. So there are many things you can do. I mean, mini programming language that allows you to write in a language what is it that you could want to find, if it's a bug or not a bug, or nice interfaces, web interfaces, or use some of the tools I suggested, right? Just don't come and show me something very simple that took only 3 hours in an afternoon to build. Right? So what I want to do is to see that you put some effort into building some useful thing based on the experience you already have with the other projects. Think about debugging your own projects. This is really what I want you to do. Build a tool that would have helped you find bugs. And if you actually find bugs in your own program, even after submission, I'm not going to take points off, by the way, then that basically is much better. Right? That means a tool like this would have been critical if you really wanted to produce a good version of the software before. All right? Okay, and happy Thanksgiving, which is coming in about 2 days, right? And keep on coding on that project.